Hi viewers, welcome to our YouTube channel. In today's video, we are going to introduce the most interesting topic, which is vectors. So I believe some of you, it's your first time coming across this YouTube channel. So try to subscribe to our channel. Before we proceed, try to like the video, share with your friends, and leave a comment if it is making sense to you. So as we're trying to introduce vectors, we need to look at the most important parts only. Actually, we are going to concentrate more on how a vector is going to be resolved into its components. Specifically, we are talking about a two-dimensional vector. By definition, a vector is a quantity which has both the magnitude and direction. So if I'm trying to draw here, I understand that from this given point to that given position, the line which is made in the middle describes what a vector is by having an arrow pointing in that given direction. So I'll say this is vector A. I'll put a bar on top. That is what we call a vector. Now, since it has been drawn in a slant direction, we are going to understand that whatever you put on this given position and whatever I'm going to put on that given position, these are what we call the components. What names or components do you have? In this case, we have the x component as well as the y component. Most of the times this happens on an x or y plane if a vector has been raised at a given direction, which is that. Now, if we say it has both magnitude and direction, what's the meaning of that? That actually simply means the magnitude has to be the actual change from this given position to that given position. That's what we call magnitude. And then if we talk of what we call the direction, it has to be the angle which is going to be made between a certain axis and the same line which is making the magnitude. We can have the angle on this given position, or we are going to have the angle on that given position. But when referring to the definition itself, if we talk of direction, direction has to be the angle which is made between positive x-axis, which is also located somewhere there. I'll say this is positive x, that is positive y, this is negative x, that is negative y. So try to pay attention on how we can get the actual direction. The actual direction, in other ways, we call it as an actual angle. So the actual angle, or rather the direction of each and every vector, is the angle which is made between the positive x-axis and the magnitude and the location where the magnitude is, or the location where the vector is. How do you move for you to come up with the actual angle? The actual angle, I repeat, I said it has to be the angle made between positive x-axis and where the vector is if you move in the anti-clockwise direction, not clockwise direction, no, because it's possible I can move in this given direction. Someone will say I've made an angle between positive x-axis and the magnitude of a given vector. So most of the times we get the angle, or rather the actual angle. In other ways, I'll say direction, by moving from positive x-axis to where the vector is in the anti-clockwise direction. That angle which is made between the same x-axis and the magnitude of a given vector, that's what we call the actual angle for that specific vector. So in this case, if you have a resultant like this one, you find that the angle which is made between positive x-axis and where the vector is, if I move in the anti-clockwise direction, that's what we call the actual angle that is going to be used whenever you want to do calculations. So basically we have a number of examples that belongs to vectors. Let me try to list down the same examples. All right, we are back again. We try to proceed. So these are some of the examples of vectors. That actually simply means whatever you have on this given position, we can even have a force, and it has to be a vector. Resultant, it can either be force, velocity, displacement, or acceleration, but you need to make sure that you know the SI units for each and every type of a vector that you are dealing with. Now, I'm trying to concentrate much on how a vector can be resolved into its components, on how you can resolve a given vector which is having a direction theta. Remember, I said direction, we're supposed to have the angle which is made between positive x-axis and where the vector is located if you move in the anticlockwise direction. So how can you resolve this given vector into its components? What are the same components are we talking about? We're talking about the component in the x-axis and also the component in the y-axis. Same applies even on this simple illustration. We are going to have the component in the x-axis and the component in the y-axis. Remember, we are dealing with the component first of all in the positive axis only. This is in y as well as in the x axis. So how can you resolve? You need to recall, or you need to remember always, as you are trying to resolve every vector into its components, you have to be able to remember this given point. So I'll write it here. I'll say, when resolving a given vector, always use the actual angle. That has to be the first point you should be able to remember. The second point, as you are trying to resolve every vector into its components, you say always use SOHCAHTOA to get the components of a given vector. I'm saying resolving a given vector, you should be able to use the actual angle. That is the angle between positive x-axis and where the vector is located if you move in the anticlockwise direction. The third point that you can also recall as you're trying to do some sorts of resolving of a given vector. Since we are using SOHCAHTOA, from grade 12, you learned that SOHCAHTOA simply means sine theta is equal to, in short, SOHCAHTOA simply means this part has to be sine opposite hypotenuse, then CA car, which is cos adjacent hypotenuse, and TOA simply means tangent opposite adjacent. So when resolving each and every vector, we always use these two identities, the identity for cos and the identity for what? For sine. Then whenever you want to get back to the issue of direction, if you want to get the angle which is here, that's when now we're supposed to use what we call tangent. So what are we going to do on the third point? So I'll say always put an identity of cosine on the x component and sine identity on the y component. Why are we trying to put these things like this? It's because always x is the one which is making the actual angle and where the vector is located if I move in the anticlockwise direction. So all what you're supposed to do is you have to put cosine on the part of x axis, or rather x component, and sine on the part of y component. Let's try to resolve this given vector and see how we are going to get the same components. If I have a given vector located somewhere there, I'll use a resultant r, then this vector is raised at an angle of theta. So whenever you want to resolve that given vector into its components, what you are supposed to understand here is the component in the x-axis must have an identity of cosine, and the component in the y-axis must have an identity of sine. Why are we doing this? Is because if you use actual angles, you are supposed to get the actual angle between positive x-axis and where the resultant is, or rather where the magnitude of a given vector is located. So here we are going to have the x component of the resultant and the y component of the resultant. So since I'm trying to resolve this one which is there, all what you need to do is I'm going to have something like this. I'll put the resultant itself, then in front of it write the identity of what? Cosine, which is cos theta. Then somewhere there we're supposed to do the same. I'm going to put in front the identity of sine theta on the y-axis. So sometimes what they're going to do, they'll give you a resultant, or rather a vector, then what they're going to do, they're going to put an angle somewhere there, which is theta. So according to what I'm from saying, always you have to get the actual angle if you want to resolve this given vector. To avoid confusion, it's better you get the actual angle for that given vector. So in the first quadrant, if you've been given something like this, all what you need to recall is that you can get the angle which is going to be made between positive x-axis and where the magnitude is by subtracting this given angle from 90. That's when you are going to consider the actual way of resolving, which is illustrated on top somewhere there. Now, the question is, what can you do in a case whereby you have a lot of vectors that are acting on one point, but they're having different angles? That name we can give to that type of a vector is what we call coplanar. So coplanar vectors, these are supposed to be vectors that are acting on one point. Actually, we are talking about the origin. These are vectors that are acting on the origin. So how can you come up with their actual angles? How can you come up with their actual angles? Let's try to check from the following diagram. We proceed. So this is one of the diagrams that requires you to understand what we call coplanar vectors, vectors that are starting from one point. Specifically, we're talking about the origin. Now, in this case, you understand a lot of things that are just being displayed on this very diagram. If you check, we have certain vectors that are pointing in axes, and we have certain vectors that are raised at a given angles. We have theta 1, theta 2, theta 3, and theta 4. Now, since I'm talking about the directions are supposed to be said to be directions whenever you have the actual angle. So each and every vector must first of all have the actual angle. How are we going to get the same actual angles? We said an actual angle has to be the angle which is made between positive x-axis and where the vector is if I move in the anticlockwise direction. So in this case, if I start from this very point, vector A, the actual angle for vector A has to be 0 degrees or 360 degrees. Why? Because it is already pointing towards the x-axis where the angle here is said to be 0 degrees. The angle there is said to be 90 degrees. The angle here is said to be 180 degrees. The angle somewhere there is said to be 270 degrees, and finally on this part it has to be 360 degrees. So the actual angle for this one, no matter what, you can't move in the anticlockwise direction. Why? Because this is already lying in the x-axis, and the angle for this guy is going to be 0 degrees. So I'll say actual angle for this one has to be 0 degrees, meaning that when resolving this guy into its components, all what we are going to have is we need to have the x-axis or the x component and the y component using the 0 degrees which is there. So if you have x-axis and y on that given position, for this vector, whenever we want to resolve it into its components, we're supposed to have a cos 0 degrees, because we said always in the x component we're supposed to have cosine if we are using the actual angle. Then in y we're supposed to have a, the opposite identity is sine 0 degrees. So a must be a vector, it has to be a number. It will either be magnitude of displacement, magnitude of force, acceleration, or velocity, and that's what you're supposed to put here. Meaning that even the components themselves, they're supposed to have the actual SI units for that very vector you're dealing with. Same applies even on this part. Meaning that you're done with this part if you're trying to resolve this guy into its components. But most of the times you are supposed to start by getting the actual angles for each and every vector in a case where they've given you this type of arrangement. Then you come to this vector, which is vector B. For vector B, what are we supposed to do? For vector B, what are we supposed to do for us to come up with the actual angle for that very vector? So since we are saying the actual angle has to be the angle made between positive x-axis and where the vector is, if I move in the anticlockwise direction, we are going to notice that the vector which is located somewhere there, vector B, will have its actual angle as theta 1. Why? Because that is the angle made between positive x-axis and where the vector is. So even when resolving this into its components, x and y component, we are going to notice that it will have something like this: b cos theta 1 and b sine theta 1. This is for x-axis, that is for y-axis. Theta 1 has to be the angle, theta 1 is the angle, and b is going to be the given vector. If I go to the third vector, which is moving or which is along the y-axis, we are going to notice that this vector, that vector, and this vector, they always have their actual angle based on the direction they're taking, and the direction for this one is moving towards 90 degrees. So you won't even suffer for you to come up with the actual angle for this. It will actually be 90 degrees. So I'll say this one 90 degrees. Resolving it into its components, we are going to notice that it will be C cos 90 and C sine 90. Very simple and straightforward. If I come to this one, which is having theta 2 located on this given position, what do you do? From grade 12, I think you did, what's this? Angles on a straight line, angles that are right angled, that are forming a right angled triangle, 60 degrees, what. So even here we are going to be using the same concept. How can you use it? Remember, I said for you to resolve each and every vector, you are supposed to start by getting the actual angle. How can you get the actual angle in this case? The actual angle can only be found if you have an angle between positive x-axis and where the vector is located if you move in the anticlockwise direction. So moving in the anticlockwise direction, what are we going to do for us to get the angle which is made on this given part, the angle which is made somewhere there? So for me to get the angle which is made on that given position, all what I need to do is I'll say my angle theta has to be equal to 180 minus theta 2, and that will be the actual angle for vector D, meaning that whatever you get on this part, that's what you are going to use for you to resolve the vector located somewhere there into its components. So I'll say the actual angle for vector D has to be 180 minus theta 2. Very simple and straightforward. Then vector E is already moving along the x-axis towards 180 degrees. Its actual angle has to be equal to what? 180 degrees. Okay, if we try to proceed again, we move to vector F. Vector F is raised at a certain angle, theta 3. So what am I supposed to do for me to come up with the actual angle for vector F? Remember, we said always the actual angle has to be the angle made between positive x-axis and where the vector is if you move in the anticlockwise direction. So meaning that the actual angle for this one has to be the angle which is going to be bam. So for me to come up with the angle which is going to be made somewhere there, what do? You have to subtract the theta located here from 270 degrees, meaning that actual angle for vector F has to be equal to, this one has to be 270 minus theta 3. This is what we are going to use whenever we want to resolve the vector F into its components. If you come to vector G, actually it is pointing towards 270 degrees, meaning that vector G will have its actual angle as 270 degrees. Try to find the actual angle for vector H. So for this one, we are going to do the same. The angle made between positive x-axis and where the vector is. If I move in the anticlockwise direction, you'll find that that's what we are going to have as the actual angle. In this case, the actual angle for vector H has to be equal to 360 minus theta 4. This is what we are going to use to resolve this guy into its components. That's what we are going to do for us to resolve the guy located there into its components. Now, all these components can be combined and we can come up with one resultant, or rather the magnitude of the resultant for all these vectors. How do you get the so-called resultant for all these vectors? Remember, for me to come up with the resultant, I need to get the resultant in the x component and the resultant in the y component. Let me try to demonstrate on a table how these vectors are going to be aligned on a table. So actually, before I go to the part of a table, we have a number of methods that you can use whenever you want to come up with the magnitude of a given vector or a magnitude of a given number of vectors. And what is that same method? So some people will call it as analytical method or component method. And that is the commonest method we are going to be using whenever you want to get the magnitude of a certain number of vectors. So what I'm going to do here, I will draw a table, which is analytical method or component method, where I'm going to arrange all the components and try by all means to come up with the formula you can use to get what we call the magnitude and the direction for the same resultant for all the forces. So let me try to draw a simple table here. Let me try to draw a simple table there. Okay, so this table is going to have 3 columns. The number of rows are supposed to be depending on the number of vectors that you have. Number of rows supposed to be depending on the number of vectors that you have. Okay, I'll write it like this. So here I'll say vector, and here I'll say x component. Somewhere there I'll say y component. Now, I'll try to get back a bit to this. So I'm going to pick 4 different vectors from this, and their angles, I'll label them as theta 1, theta 2, theta 3. And the same angles are going to be my actual angles. So forget a bit about whatever I illustrated on this part, but I'll just get vector A, vector B, vector what, then the angle for this, I'll label it as theta 1. Maybe the angle for that, I'll label it as theta 2. The angle for this one, theta 3, and that one, just like that. So here, if I have vector A, which is raised at an angle of theta 1 as the actual angle, vector B raised at an angle of theta 2, actual angle, vector C raised at an angle of theta 3, the actual angle, and vector D raised at an angle of theta 4 as an actual angle as well, meaning that we are going to have the resultant at the end for all these vectors. So remember, if you have the resultant must also have the resultant in x and y based on the components that you have. So each and every vector here is going to have the components in x and y. So if I want to get the component in x and y for this one, remember we said always the x component must have the identity of cosine, then the component in y will have the identity of what? Of sine. So we are going to have a cos theta 1, then a sine theta 1. So you can punch this at the end. Just punch this like the way it is plus whatever I'm going to write here. B cos theta 2, B sine theta 2, C cos theta 3, C sine theta 3. Then you have D cos theta 4, D sine theta 4. So we are going to have the resultant in x-axis and the resultant in the y-axis based on the components that you have. So what I'm saying is, if you've been given the vectors and you have the actual angles, same applies even here. Your calculator can work in a straightforward by punching. Maybe this is 5, that is 10. I'll say 5 cos 10 plus whatever you've been given here, cos the angle, plus whatever you've been given there, until you say equal to, it will give you the actual angle on this given position. Same applies even here. You do likewise. You punch everything to avoid getting errors. It's better you punch everything. You say plus, punch everything plus this one, that one, and it will give you the resultant in y and x. So for me to get the so-called magnitude of the resultant for all the forces, or rather vectors to say, all what we need to understand is the magnitude is always calculated using the formula. So it can be resultant as this one, or saying the magnitude of the resultant. Some people will put it like this to show that you are dealing with the magnitude. It has to be equal to root of the total sum of x component, or rather the resultant in x squared, plus the total sum of resultant in the y-axis. That's what you are supposed to use whenever you want to come up with the magnitude of the resultant. As simple as that. If you come up with that, all what you need to do is just punch or plug in everything and it will give you the answer. Whether negative, put them inside the brackets until you get a positive number. So for me to get the direction of the resultant itself, I know a resultant can be something like this. Always the resultant has to be depending on where it is located. That's when you can get the magnitude of the direction. If I do this, if my resultant is located in the first quadrant, meaning that both x-axis and y-axis, or rather y component, are having positive resultants on this part or on those two positions. That is, if your resultant is located in the first quadrant, you can only locate a resultant to be in the first quadrant if both of these two are positive. If one of these, maybe this one is negative, that one is positive, just know that to plot this, it has to be located in the second quadrant. It's more like I'm plotting x, y. So if x, y, if you have these two, just know that it will be in the first quadrant. If one of these is negative, like x, if it is negative, meaning that Rx is negative, so it has to be negative x, y, it will be located in the second quadrant. So how do you get the actual angle for this vector and that given vector? For me to start the journey of getting the so-called direction. Here, if it is located in the first quadrant, your angle will just be made on this part. So what we're going to use here, it has to be the identity of tangent. Now, this is where tangent is supposed to be applied. So tan has to be the resultant in the y over the resultant in the x. Then you know what you're supposed to do. You did this for grade 12. Okay. Now, if it is located in the second quadrant, what do you do? Just know that one component is having a negative. So when plugging in on the part of tan, you always ignore the negative. You always ignore the negative, meaning that I'm going to punch, I'm going to consider this one to be positive and that one to be positive first of all. Then after getting the angle you are going to get, if you consider this one to be positive and that one to be positive, using the formula which is here, the angle you get has to be the one which is going to be somewhere there between negative x-axis and that one. So you come back to the actual angle. How do you get the actual angle? We said you're supposed to have the actual angle as the angle made between positive x-axis and where the resultant is located if you move in the anticlockwise direction. So you start by getting the angle which is going to have positive axis. You always consider this one to be negative first of all if you want to start with the angle that is going to be made between this and that, or rather the angle which is made for which is being calculated using the two resultants in the x and y. If your resultant is located in the third quadrant, that actually simply means both of this and that one are supposed to have negative axes. So we are going to have negative x and negative y. Same, even here when plugging in into that, you need to start by considering these two as positive. The negatives will only help you identify the location of where that same resultant is found. So I'm going to consider this one and that one to be positive as I'm trying to use tan. Remember, tan is not used anyhow. You're supposed to consider both of the axes as positives. So I'm going to take this one to be positive, that one to be positive. Whatever angle I'm going to get on this part has to be the angle which is going to be located here. Remember, when you punch everything on the tan, it will give you the angle which is made between x-axis and where the vector is. So even here, it had to be x-axis and where the vector is, but the actual angle, you always get the actual angle between positive x-axis and where the vector is if I move in the anticlockwise direction. Meaning that if you get your theta to be located somewhere there, all what you need to do is you can get the actual angle for, or you can get the direction now for the given resultant you're going to get by saying theta as the actual angle equal to 180 plus whatever you're going to calculate if you consider this one and that one to be positives. Same applies to this part. If your resultant is located in the fourth quadrant, just know that one axis here is supposed to be positive and that has to be x, the other one has to be negative. So we're talking about these two resultants in x and y. If this one is positive, that one is negative, just know that your resultant is going to be located in the fourth quadrant. So what do you do? The thing you're supposed to do in this case has to be consider the negative which is here as positive whenever you are trying to punch into that. So Rx you put there, Ry you take it on that part, and you are going to get your angle if these two are going to be considered as positives. The angle you're going to get has to be between x-axis and where the vector is. But the actual angle now, that's when you consider positive x and where the vector is if I move in the anticlockwise direction until I touch that given vector. That's what you're going to get as the actual angle. So we have a lot under vectors that we are supposed to consider. We have a lot of things that we're supposed to consider under vectors. How to read some of the vectors that are given in a form of a statement, unlike in a form of what? In a form of a diagram. And what are the same two ways? So you can be given a question which is going to be like this, or you can be given a question which is going to come with vectors like this. If a given vector is said to have this type of description, how can you write that same vector on an x or y plane? If they're saying a vector has north of east, any vector which is said to have something like this, maybe 50 newtons, then they'll give you an angle 50 newtons, 30 degrees north of east. How can you write, or how can you plot this given vector? Whatever you've been given in a question is just a simple statement. How can you plot that same thing on an x or y plane? So I'll say this is east, that is north, this is west, that is south. So for me to plot this one on this diagram, and then I come up with the actual angle, how can you plot? Just know that your vector is located between north and east. But how can you write this angle? If we see something like north of east, just know that you are supposed to cover 30 degrees from the last pole to be mentioned towards the first pole you've been given. So in this case, we are going to cover 30 degrees towards north, and then my vector is going to start from here. This is where we're supposed to put our 30 degrees. I'll write my 50 newtons on this part. What if they write it like this? 50 newtons northeast. If they say 50 degrees northeast, always those poles, if they are combined like this, just know that the angle which is made between two different poles has to be divided in the middle. So our vector is going to divide these two poles in the middle, meaning that it has to divide this angle made here into half. So the angle we are going to get, it has to be 45 degrees. So for this one, it comes in, if you have north of east, you always start from the last pole to be mentioned, going towards the one which has been mentioned first, covering a certain angle you've been given. If they say northeast, just know that you are supposed to move, or you are supposed to divide a certain quadrant into half of its angle, and this is what we are going to get if I move in that given direction. So if they say north of west, just know that you're supposed to move from westward going towards north, covering a certain angle you've been given. If they're saying 30 degrees north of west, what do? We're supposed to move from west going towards north, covering an angle of what? 30 degrees. Very simple and straightforward. So a question is going to come in this format, and you have to illustrate it on a vein, on an x or y plane. After illustrating it on an x or y plane, now you need to come up with the actual angles for each and every vector for you to resolve this vector into its components. Then there is one thing again. If they say north 30 degrees east, try to differentiate between these two. 30 degrees north of east means you are starting from the last pole to be mentioned, going towards the first pole, covering the angle you've been given. That's what you're going to write. If they put the angle between two different poles, what do? Here is something which is straightforward. You always start from the first pole to be mentioned, going to the second pole. So differentiate between this, which is having of in the middle, whereby they're saying 30 degrees north of east, and if they say north 30 degrees east, you are supposed to do what? Start from here going like that, and it will be something which is going to be straightforward. Just have to say, you put your vector there, you put the angle based on this illustration. This is what I wanted to give you guys again before we close this session. So as I'm going to teach you, having the physical lesson, you're supposed to understand that things move hand in hand when it comes to the issue of resolving. And don't forget to understand what is being described on this given part. So try to subscribe to our channel, try to share with your friends, and leave a comment on this very video. Thank you very much.